All right, let's get started. So today we're going to be talking a little bit more about MCMC, and then what we'll do is transition to a discussion of Bayesian inference. And we're going to sort of dive into the topic of Bayesian inference through a very specific application, which is that of topic modeling. Topic modeling is sort of like it's sort of a funny sub-area of machine learning. It's somewhere in between like a set of applications and a set of methods. And so we'll be kind of talking about that as an example of how one would do Bayesian inference. One announcement here is just that on Friday we don't have a recitation. Instead, we're going to have some project team office hours. Is this room 5222? Did I get that right? Maybe. No one knows what room we're in. Okay, that's okay. So we're going to be in this room on Friday from not 1:30 but 1:45 to 2:50. And the whole point is that we'll just be around to kind of have some informal discussion around with classmates and core staff around project ideas and such. And so I plan to, I have a draft of kind of some project directions that I'll probably post today or tomorrow so that you can kind of look through that before Friday. And yeah, so that's the newest thing on the agenda here. All right. So last time we left off talking about the Metropolis-Hastings algorithm, and I'm just going to jump back to the actual notes that we were looking at last time, just so we can see where we had left off. And so here we were thinking about this Metropolis algorithm, and the whole idea of the Metropolis algorithm was that we could choose a proposal distribution and use that proposal distribution to give us sort of a next possible sample that we might work with. And from there, just copy this over. Okay, so using a proposal distribution in this way allows us to take samples of new potential states that we could treat as samples. And like a rejection sampler, we compute some acceptance probability, which in this case was the min of 1 and the probability of the new sample, or the ratio of the probabilities of the new sample to the current state. And then we accept with that probability. So what this means is that if the, so it's important to look carefully at what this acceptance probability is actually saying to us. So namely, if the new state X is more probable than our current Xi, this is telling us that we should always accept it. That's essentially what this algorithm is saying. Okay. But if it's not more probable, well then we actually need to look at the ratio of the probabilities, and we're only going to accept it with some fractional probability. Okay. And so the Metropolis-Hastings algorithm, we said, was just like the Metropolis algorithm, except that we changed the actual computation of the acceptance probability to take into account the relative ratio of the current to new states. And so by including this factor, we're now recognizing that some samples might be sort of coming up too frequently, and we need to account for that by looking at the actual proposal distribution. Okay. So in thinking about this algorithm, it's useful to kind of understand the actual behavior of this thing from the perspective of a random walk. So here, if we have some generic proposal distribution for Metropolis-Hastings, like say a Gaussian distribution with mean 0 and some variance sigma squared, then we could basically think about this as working for pretty much any sort of continuous valued variable x, right? And the thing that we can then reason about is how the actual sampler would sort of move about in this space as a function of the proposal distribution, right? So, so the two cases that are interesting are one where epsilon, the variance here, is large. So in that case, essentially the actual sort of region from which most of the samples is going to be drawn is a really large region. Okay. And so if you have some probability distribution, say in this picture P of x, where it's given by some contour plot like the one shown, and we can say that the majority of the probability mass is concentrated inside sort of this red area. Well, so if we had a really large epsilon, then essentially that's kind of like thinking about a Q distribution that gives us a really large region to draw samples from. Now, of course, this is all probabilistic, right? A Gaussian is actually giving some probability mass to every value of x. But you can think that most of them are going to be within, say, 2 standard deviations of your current sample. And so, oh, and I should be careful here. So we could say, not that the, here, the Gaussian distribution, the way that I wrote it, it's actually always centered at 0. So this means that it's not actually like changing with the value. So really what we should do here is say, okay, let's add xt here. Okay, or we could have had a Gaussian centered at xt, right? So that wherever your current sample is, you're actually looking in sort of a neighborhood around it. And the point is that if the neighborhood is large, you might step way outside the high probability region and get a lot of rejections. Okay? And so this is very unproductive for the Metropolis-Hastings sampler. Whereas if epsilon is very small, then you might not reject very often, but you're not going to make much progress either. Because maybe all of the steps that you're taking are going to be really tiny steps. Okay, so for rejection sampling, the accepted samples are actually independent. And the reason for that is that the proposal distribution doesn't depend on the current state. So going back to my example here, right, before I added the plus xt, that would be kind of like a rejection sampler. This is just some generic proposal distribution that doesn't condition on the current state. It's just a distribution over x's. But once we condition on xt in an informative way, now we get this random walk behavior. Okay. So this is kind of the key contrast between our rejection sampler and Metropolis-Hastings, is that Metropolis-Hastings has this sequence of steps in the random walk that are actually correlated. Okay. And so the big question then that a user of a Markov chain Monte Carlo method is going to ask, how long do I have to wait until I get effectively independent samples? And unfortunately, that's not an easy question to answer. And it is going to depend heavily on how your proposal distribution relates to the actual true distribution, for the reasons about epsilon that we just described. Okay, so if we have a Gaussian proposal distribution, then what we could say is that independent states in the Metropolis-Hastings walk are separated roughly by sigma max over sigma min squared steps. Okay, and the reason for that is that if you think of where here, sigma max is going to be sort of the large variance direction of P of x, and sigma min is going to be the small variance direction of P of x, right? This is in a two-dimensional case, right? And the random walk, in order to get independent states, essentially needs to be moving almost entirely across the actual high probability region. Okay, so now we can actually think about Gibbs sampling in terms of it being a Metropolis-Hastings algorithm. So this is useful for a couple reasons. One, it allows us to recognize that Gibbs sampling is going to have that same random walk behavior as Metropolis-Hastings. It's just going to be slightly different in that the Gibbs sampler is going to take these sort of axis-aligned steps when it's making its random walk, because it's only updating the value of one variable at a time. Okay. So let's actually sort of think through how we could write Gibbs sampling as Metropolis-Hastings. So okay, so the idea here is that we can actually write down the acceptance probability, or an acceptance probability for Metropolis-Hastings as we did before. Okay, so this is just going to be copying down our definition of this acceptance probability. So this is min of 1, and exactly what we have up here. So some tilde P of x divided by, P of xi. That's another tilde. Times the ratio of qx given qxi divided by qxi given qx. So looking in both directions. Okay. So what we want to think about is, what do these quantities actually look like for the Gibbs sampler? Okay. Well, let's start substituting some quantities in. So first, let's say, this ratio of p tilde x and p tilde xi, that ratio is equal to p of x and p of xi. So not necessarily, I'm not claiming that we can necessarily compute the exact ratio of p tilde and p tilde xi, but just that it's something that we can write down, and we can reason about the fact that these two quantities are identical. And then the ratio of the q's, we can also write down what the proposal distribution for a Gibbs sampler is. Okay, so this part is where things get interesting. So does anyone want to sort of take a guess at what the proposal distribution for a Gibbs sampler is? So I think I said before, I kind of gave you the hint that Gibbs sampling is just Metropolis-Hastings, but it always accepts. So what would the proposal distribution of the Gibbs sampler be? What is Q here? So Q of x given xi equal what? So remember in Metropolis-Hastings, the idea is that you propose some new state x from Q of x given xi. And what I want is to get some probability that we would use for proposing states out of the Gibbs sample.
So do we need to make it 1 because we are already accepting?
So here, it's not that the proposal distribution itself needs to be equal to 1. What's going to end up being 1 is the ratio.
Yeah, the whole thing needs to be.
Yeah, exactly. Exactly. So the question is just, how do we define this Q?
We can take that to be P of xi.
P of, let's be careful about our indexing here. So xi is the full, so these are vectors.
So I'm just saying take the numerator by denominator to be the, so like to take numerator, the denominator to be the numerator and the.
Oh, you're saying just make sure that, well, yeah, so we definitely want these two to be equal. That's going to make sure that things work out to be 1. Okay, but the question is, how could we define Q so that it sort of mirrors what we are doing in a Gibbs sampler?
Would it be equal to Q of xi plus 1?
Q of xi plus 1. So the point is that we need to define what Q is. So here what we're actually trying to do is say, like Q is just some function that you come up with. So one example of a Q is like a Gaussian distribution. So you could set it equal to a Gaussian distribution, or it could be equal to, I don't know, a Dirichlet, or it could be equal to some other distribution that you might like.
Can we keep it as uniform?
So
That's metric.
So this is an interesting option. So if it's uniform, so remember here that we need to be really careful because we need this entire quantity to be equal to 1, not just this ratio. So really what I'm asking you to do is think about operationally, what is Gibbs sampling actually doing? Like what does a sample from Gibbs sampling look like? Right? Like how do we get from one state in a Gibbs sampler to the next state? Let's maybe go back. Look at that. So this is what we wrote down as our algorithms for Gibbs sampling. So how are we sampling the next state?
According to the full condition.
Yeah, not just the full conditional, but basically one of the variables comes from the full conditional, and then all the other variable values are just kept exactly the same. Okay, so here, this first algorithm definition Yeah, it looked, when we wrote it down, right, like we did this kind of complicated indexing, it kind of looked more complicated than it needed to be, so then we rewrote it like this, right? But now that we're looking at the first algorithmic definition, we can see really clearly what's going on with those xi's and those xi plus 1s, right? The xi plus 1 is exactly the same as xi, except for we changed one variable with a full conditional. Okay, so now let's jump ahead and try to write that down for q of xi. So we could do something, and here I'll just do some horrid use of notation to say that what we're going to get back is this sort of combination of things, which is xt is going to be randomly sampled from the full conditional. So this is xt given xi for all of the variables that are not t. And then x not t is just going to be set deterministically equal to the vector xi not t. So, so this is our proposal distribution, and the probability of transitioning to that new sample, all we need to do is take into account the deterministic part happens with probability 1. So all we need to take into account is this top part, which is the actual full conditional, right? So the probability of a given proposal is going to be the ratio of, it looks like I mixed up, even though like this was right above, I actually mixed up the indices of our i's, right? So you'll notice that in my Q ratio here, I actually have this upside down. So let's fix that. So what we meant to do here was this is xi in the numerator, and this is xi in the denominator. Okay. So now when we write out the proposal ratio, so Q, let's do the denominator first. So Q of x given xi, that's just going to be our full conditional, P of xt given xi not t. And then the numerator is going to be going in the other direction for the full conditional, right? Which is essentially sampling the value back to the to whatever xit was. So that would be xti, probability of xti given x without the I, not t. So all of the variables except for xt. All right. So now we have this ratio, and what we can do is rewrite this thing, but expand out the term p of x and p of xi. So namely, we can expand this out to be written in terms of the variable xt. Okay, so specifically think about, so what I'm about to do here is we're going to basically say if you have some distribution over p of x and y, that's just equal to p of x times p of y given x. So let's do that for this vector value distribution. Okay, so what we get back is something like p of xt given x not t. Okay, that actually looks just like a full conditional times p of x not t. Okay. Divided by the same thing but now with i's. P of xti given x not ti times p of x not ti. And then this part we can just copy right down. This will just use as it is, so this is just the ratio of the full condition. So P of xti given x not t divided by P of xt given xi not t. So all I did was I just sort of treated this as a distribution over xt and then everything else to break it up. Okay, so does anybody see what our next step is? How do we simplify this? What's the relationship between the quantity x not t and x not t superscript I? They're exactly the same, right? Because when you propose a new quantity, you're keeping those parts exactly the same. You only changed one variable, xt. So if these are exactly the same, well then, in that case, we can just take this whole thing and we can say, well, these two quantities, they are equal to, so this whole thing is equal to 1, right? It's just the probability of x naught t and divided by the probability of x naught t, right? And then here, the thing that we need to be careful of is this xt and this xti, those might actually be different, right? So, namely, so we could write that down. So xt does not necessarily equal xti. So to cancel out the remaining terms here, we need to take this and this, those two cancel, and this and this, and those two cancel. Okay. So what we're left with is this whole thing is the min of 1 and 1. Let's circle these just so we're abundantly clear here. So this blue box plus this blue box go to 1, and this red box and this red box. So this whole thing, we can see now that the acceptance probability, no matter what the value of xt and xti, is always going to be 1. And so Gibbs sampling is just the Metropolis-Hastings algorithm, where our proposal is defined like that, and where, because of our proposal distribution being of this particular form, we always accept.
Just to be sure of the indexing here, so I and I plus 1 is the next step, right, from one stage to another, and D is basically how we index our variables.
That's right.
So can you just repeat the Q sampler or the distribution?
Yeah. So you could. So let's think of this. I think I'll actually have this on a slide. This little picture of like, we have some x here, right? And how do we get there? Well, we get there by starting at some vector xi, which is some other state. And the process of getting from one to the other is by following that Q distribution. Okay, that conditions on the xi to get a sample x. Okay. So there's many possible x's that we could have landed at, but we sampled 1 from that Q, which was the specific X. So what we're saying when we talk about this Q of X given Xi for the Gibbs sampler specifically, so I guess maybe the better thing to think about is, you know, when we were talking about, now let's jump back here. So when we were talking about Metropolis-Hastings, let's actually sort of visualize how does this actually work, right? So you're at some xt, right? That's this point. So this here is xt. And then you resample some new x, okay? Let's say you sample this value of x, okay? Now, there's some probability that you'll accept it, some probability that you'll reject it. Let's suppose here that you actually do accept it. So it becomes xt plus 1. Bummer. So the T and I thing. Okay. I switched my notes to I, and I didn't actually update the slides, didn't I? Okay, so here T is equal to I. Sorry, like here I've swapped. Sorry about that. The point is that the superscript is indexing timestamp, so that ignore the actual letter itself. So what we get then is that, you know, you're gonna, from this point, propose some new point, maybe this one, and maybe it gets rejected. So then xt plus 2 is just the same as xt plus 1 because we stay at the same place. Okay. And now you sample another one here. Okay, well that has really high probability, and so it gets accepted as xt plus 3. And so this process continues, and you might walk down to one side and walk back and walk across, and maybe you step outside the high probability region for a little while and then come back. So for Gibbs sampling, if you think about what we're actually doing with this proposal distribution, essentially we're saying we have two variables, say x1 and x2. And again, we can kind of think of, you know, having some probability density like this. But now, whenever we're doing the random walk, it's always going to be axis-aligned moves. You can't move diagonally. So a proposal is going to send you along an axis to some new point. And then it'll pick the other variable and send you along the axis to some new point. And then again, it'll move across the axis to some new point. And this is just going to continue. But you're always moving in an axis-aligned way.
Is the sequence going to matter?
Say that?
Like, is the sequence going to remain the same for every step? Like, first we move an x1, then we move an x2, then we do the opposite, and can keep shuffling that.
Yeah, so there's lots of variants of Gibbs sampling. So one of them is rather than iterating through the variables, you can randomly pick a variable. And so the way that we can see that this works is by looking at the properties of Markov chains that we're about to talk about. And we can just show that if you randomly pick the variable, you still satisfy this property of detailed balance, which is what we need to show that it's a valid Markov chain with the properties that we want.
But the value that so one of the variables will be in the conditional, right? So if that remains the same when we go into the next step.
Yep.
So then we probably would have to shuffle between.
Yeah, but you could imagine a setting where sometimes you take two steps along the same axis, right? And that would be a valid Gibbs sampler.
So we aren't restricting the function form of Q distribution to anything that we know that we can draw samples from easily. So are we saying that because Q is low dimensional, we can, regardless of whatever function form it takes, we can draw samples? That's what you're saying?
Yeah, right. So in a Gibbs sampler, yeah, or basically So in the Metropolis-Hastings though, let's be careful here, right? Because for Metropolis-Hastings, Q is a distribution over the entire vector X, right? So Metropolis-Hastings is a specialization where we're only resampling one variable at a time. So, okay, so then, I actually wasn't going to talk about this, but let's do a quick foray into block Gibbs sampling. So the way that block Gibbs sampling works is we say for I equals 1, 2, 3, and then and now here's where we're going to get kind of funny. We're going to say for B in a set of, so for a block in a set of blocks, we're going to resample the vector xb from the full conditional of vector xb given vector x not b. Okay, so this is sort of a generalization of the regular Gibbs sampler, except that now what we're saying is that B is not an element in the index set 1 through n, but rather B is a subset of the index set, 1 to t. Okay. So you could say this is a subset of the variable indices. Okay, and this is all the variables in the subset and all of the variables not in the subset. Okay. So basically this is now just like the Gibbs sampler that we saw before, but we're saying that you could take an entire group of variables at a time, and so long as you can compute the full conditional efficiently, then resampling here is easy. So one example of a set of blocks that you could use is the factors in your factor graph, right? So because of the structure of a factor graph, so we could set B equal to the set of factors, factor graph. Okay. And here then, what we're doing is we're resampling all of the variables that touch a particular factor, but all at once. And so this might actually have some advantages in terms of what we call mixing time, which we'll talk about in a moment. Okay, which is basically how quickly we get to the true distribution. Okay. Okay. So next we want to think about Markov chains and explain why it is that these algorithms are actually giving us samples from the distribution that we care about. Okay. So that's the big question of this section, is why is it that these algorithms are actually working? Like, don't just take my word for it that they work. Let's actually show that they work. Okay, so what's a Markov chain? So a Markov chain is sort of the building block for these algorithms. And we say that Markov chain is a random process. Okay, and what that means is that it gives a series of random variables. So a random variable can give you a set of samples from that random variable, but they'll be independent terms. A random process gives you a sequence of random variables that might be correlated in some way. Okay, so two examples of this, of a Markov chain, would be a first order Markov chain. And a first order Markov chain would be one where we say the probability, let's be specific. So a series of random variables which we'll call x superscript 1, x superscript 2, and so on up to some x superscript I, some x superscript I plus 1. So here, we want to say that a first order Markov process is going to say we have the probability of xi given all of the variables up to I. So that would be xi minus 1 all the way down to x1. That is defined to be equal to the probability of just xi given xi minus 1. So this first order Markov assumption that we're making here is the same first order Markov assumption that often shows up in things like a Markov decision process for reinforcement learning or a hidden Markov model. So we can likewise make a second order Markov chain. And a second order Markov chain would just say that the probability of the same thing here is equal to p of xi given the previous two states. So that would be xi minus 1 and xi minus 2. So whenever we talk about Markov chains, it's useful to also have this notion of transition probabilities. So the transition probabilities we're talking about for a Markov chain are just the set of probabilities that we work with to transition from one state to another. So for a first order Markov chain, we could write down that we have transition probabilities that we'll call R sub t of, we'll call them R sub I of x I plus 1 from xi. So it's the distribution over the next variable from whatever your current one is. And we're going to define that R to be the probability according to whatever our Markov chain is. So if it's a first order Markov chain, it's just the probability of xi plus 1 given xi. Okay, so why did I bother coming up with some new name for R here? Oops, sorry. Be careful about my own indexing. So here, these i's need to be, let's say, in the superscript. So this is xi plus 1 and xi. Okay. So once we have this notion of this R transition probabilities, we can say that there's such a thing as a homogeneous Markov chain, which is simply one where R sub I is always defined to be equal to some fixed R. So what this is saying is basically, if we're using R of this form, then think of the Markov chain as having the same transition probabilities at every time step. So the transition probabilities are the same for all I. So, all right, so here, we're going to now think about what it is that allows us to ensure that we set up a Markov chain such that it gives us back samples from the true distribution. So the key question here is how to define a Markov chain such that it yields samples from a desired distribution. And let's call that desired distribution some P star. So this is our key question. And so we're going to think about sort of two properties that we need here. The first required property is that we have sort of that P star is the invariant distribution of the Markov chain. So the question is just, what is an invariant distribution? So we can basically say that P star of x is the, or you could say it's invariant with respect to the Markov chain, or really not just any Markov chain, but say the transition matrix that we're going to just call R here. And you could think of this as, you know, this R is sort of fully defining our Markov chain. So we're going to say that P star is invariant with respect to a Markov chain defined by a transition matrix R if the following holds. If we have that P star of x is equal to a sum over all possible x prime, taking the probability according to R of transitioning to x from x prime times the probability P star of x prime. Or in case x is continuous, we also need to be able to write this as P star of x equals the integral of this quantity. So So these two statements are the same, just that one would be for discrete and one would be for continuous, I believe. Okay, so so if this is true, then we have that P star is the invariant distribution of the Markov chain. And so sort of the key thing is that we can consider the actual marginal of our Markov chain. So think about xi plus 1. Okay, so what do we write down? We have that p of xi plus 1. Okay, according to our Markov chain, this is a marginal probability where I just summed over all the values of xi minus 1, xi minus 2, all the way down to x1. Okay, but so this is a sum over all, x1, x2 up to x superscript 1, x superscript 2 up to x superscript I. Where we take the joint probability of all of these. Okay, that's what a marginal probability is. Okay, so here we're just summing over all of those for the joint probability. Well, that marginal probability, summing over all of these, is actually equal to a sum over just xi of p of xi plus 1 given xi times p of xi. And this is true just sort of by induction on this summation. Right? All we're saying is that this quantity is equal to, if you already had the marginal probability of just xi, to get the marginal probability of the next state, you just need to sum over all the possible next states. Oops, sorry, this summation should be over xi plus 1. Oh, no, sorry. No, that's correct. Over all xi. So sum over all possible previous states for this product of probabilities. All right, so okay, so this is required property number 1. So the second property is that the distribution we want is the equilibrium distribution for this thing. So here we say that it's the equilibrium distribution of the Markov chain. Oops. Okay, so here's how we can define an equilibrium distribution. So suppose that we're given some arbitrary initial state, x1. Doesn't matter where you start. And now, suppose further that p star of x is invariant to our transition matrix R. Okay, so suppose that the first required property holds. Okay, if that's the case, then p star of x is the equilibrium distribution if we have the following, that the limit as I goes to infinity of p star of x is, or sorry, not P star of x, but just if the limit as I goes into infinity of that marginal P of xi is equal to P star of x. So what this is saying is that, let's take a big step back here. And sorry, before we do that, let me make one more annoying definition, which is just that if this is the case, then the Markov chain is said to be ergodic. Okay, so what did we just accomplish? We said that you can reason about the marginal distribution of some future state from your Markov chain. Imagine that you have a Gibbs sampler, and you start out, all the way back at some state x1. Okay, and then who knows how you do it? You take a bunch of steps through different states, and you move all over the place, and you end up at some state xi. Okay. We could ask the question, what is one of these days I'm just gonna stop supporting the online section and make them all show up. The problem is none of you have dropped. We really counted on having the ability to fit everybody in this room, but there's still somehow 60 people in this class. Despite the attendance, we should probably did we ever invite online section people to fill in empty seats?
I don't think so.
Okay, we should do that. Can you do that now?
Yeah, I can do that.
So basically, imagine that you start at some state x1, and then you take a bunch of steps and you land at state xi. Okay, that's one possible xi. But there's lots of other xi's that you could have landed at. And you could reason about the distribution over future states xi that you could land at, right? And so what we're saying here is that the first property is that we need it to be the case that whatever the P star distribution is, it's going to be invariant to transitions in our according to our Markov chain. So if you already have a distribution over the states xi that is identical to P star, okay, and now we say let's just take a sample from P star of xi, but now take one more step from your Markov chain. The first property is saying that that will be the exact same distribution as P star of x. Okay, so a sample from P star plus one step of your Markov chain is a sample from P star. Okay, the second part here doesn't even say that it's giving me an error. That's the worst part. See if we can get something showing up here. It's not true. It hasn't synced just now. Okay, so the second statement, the equilibrium distribution statement, is saying that as I increases, as we take more and more steps in this Markov chain, the marginal distribution, P of xi, is approaching P star of x, the distribution that we actually want. Okay. Okay, so, yep.
So, one more question. You said that when we talk about MC, it's good to introduce transition probabilities. But is that the only reason we're talking about transition?
So is that the only reason that we're talking about transition probabilities? Oh no, sorry, so.
Introduce the idea.
So the transition probabilities were always there. I just wanted a different notion of a transition matrix, so that I could talk about. So basically, we have a lot of like letters going on here, right? So the whole reason that we introduced this notion of a transition matrix R was so that I would be able to actually like talk about the actual transition probability distribution as like something very distinct from, say, P star. Basically, we just started accumulating too many things with the letter P. So that was the only reason that I introduced the transition probabilities as R, just so that it's really clear where the actual Markov chain is showing up in these equations. Yeah.
And just another question.
Sure.
So in the property number 1, is it only true if we're talking about the first order Markov chain, or does it work others?
Oh, sorry. So yeah, so here we are, sorry, I didn't make that clear. So we are assuming that we're working with a first order homogeneous Markov chain. Sorry, that was my assumption.
So one won't be the other.
Just that we need to change the statements a little bit, right? Because the way that we actually wrote the statements for required property 1 was in terms of this transition matrix. So we would have had to write it in terms of something that conditioned on multiple states, and then we would have had to marginalize over multiple states. Okay. So we can do it. Here we're just doing it for the first order homogeneous case, which is going to be true of the that those assumptions are going to hold for Gibbs samplers and for Metropolis-Hastings algorithms. Okay, so the last detail here is that so we don't actually have to sort of directly prove these properties. Instead, we can work with sufficient conditions for them. And so these sufficient conditions are going to be that, let's see if we can make something happen. We should just end class early due to technical difficulties and call it a day. Okay, so we'll just jump over here and we'll just pretend that all of the things that I wrote didn't actually ever make it. So the key limit thing that just is not showing up for some reason is the limit of this marginal distribution is equal to P star of x. That's all. Okay, so what are the sufficient conditions here? So the sufficient conditions for these required properties are twofold. One, we say that R satisfies detailed balance if the following holds, which is that R of x prime from x times P star of x is equal to the reverse direction, which is R of x from x prime P star of x prime. So that's the property of detailed balance, and detailed balance actually implies that P star is invariant with respect to R. Okay. So if you can show that for whatever P star is, taking a step, and then just take two states, x and x prime. And if you can show that taking a step from x to x prime, according to your Markov chain, has the same probability as taking a step from x prime to x, where you're factoring in the relative probability of those two, of the P star distribution landing in those states, then that actually guarantees this invariant property that we set out before. Okay, so the second sufficient condition is that if P star of x is invariant with respect to R, and the following property holds, then we're going to get back an equilibrium distribution just as we wanted. So if we have that V is equal to the min over x and x prime, such that I'll come back to the such that in just a second. So taking the min over x and x prime of the transition probability of moving to x prime from x divided by the true probability of x. So if this whole thing is greater than 0, then P star is going to be the equilibrium distribution. Okay, but we need to be careful here because when we're looking at all x and x prime, we need to make sure that we're only thinking about cases such that P star of x is greater than 0. Okay. Right, so we don't want the denominator to be 0. Okay. So what is this minimum actually telling us? It's telling us, looking at all possible pairs of states, think about, what is the smallest ratio of a transition probability from x to x prime divided by the probability of x. And we're saying so long as that ratio, whatever the smallest such ratio there is greater than 0, then we have that P star is the equilibrium distribution for R. Okay. So these are the two properties that we end up caring about for Metropolis-Hastings. And so now we can actually tie this all back to the algorithm. So the transition probabilities, or the transition matrix for Metropolis-Hastings, we could actually write that out. Right? Like, what does the transition matrix of pairs of states, x from state xi, what does that actually look like? So what's the probability of transitioning to some state x from some state xi in Metropolis-Hastings? So there's going to be a ratio in there, but what? Yeah, so this should just be Q of x given xi, right? Okay, did we leave anything out? So you take a proposal from Q of xi, or Q of x given xi. Do you always keep state x? Do you always transition there?
With acceptance probability.
Yeah, we need to multiply in the acceptance probability, right? You're only going to transition to x from xi if you sample it with this probability and you accept with probability min of 1 and that obnoxious ratio p of x over p of xi times q of xi given x divided by q of x given xi. Okay, so this whole thing is a definition of the transition matrix for Metropolis-Hastings. Okay, so from here, what we would want to do is to actually prove that Metropolis-Hastings satisfies detailed balance. Okay, so if we prove that Metropolis-Hastings with this transition matrix satisfies detailed balance, then we've effectively proved that, and I guess we'd also need to prove part 2 here, which is that that this ratio is always going to be greater than 0, and to prove that, you actually need to inspect the proposal distribution, right? Okay, so there you just need to make sure that the proposal distribution doesn't have any zero probabilities for states, right? So long as your proposal distribution always gives non-zero probability to some state, then part 2 here is easy to prove. Falls right in. Okay, so proving that this transition matrix satisfies that equation would guarantee for us that P star is invariant with respect to R and that P star is the equilibrium distribution with respect to R. Okay. So we'll have you guys do that on homework 4. Essentially that then ties together everything here because it shows us that the Metropolis-Hastings algorithm is a Markov chain, and we're just taking samples from that Markov chain. And as long as we take enough samples from it, eventually those samples, because P star is the equilibrium distribution, eventually those samples from the Markov chain will actually look just like samples from the true distribution that we care about, if you look at them in terms of their marginal probability. Okay. So this is sort of the power of this sort of collection of methods. And of course, because Gibbs sampling is a special case of Metropolis-Hastings, once you've proved this for Metropolis-Hastings, you've also proved that Gibbs sampling gives you a Markov chain that is a valid way of drawing samples from the distribution that we care about. Okay, so in words, detailed balance just means that for each pair of states, x and x prime, arriving at x and then x prime versus arriving at x prime and then at x are equal probable, right? And so if you can just prove that, then you've successfully shown that Metropolis-Hastings works. Okay. So there are some practical issues, and one of them is, is it better to move along one dimension or many? So for Metropolis-Hastings, it turns out it's actually sometimes better to sample one dimension at a time. Okay, so even though the proposal distribution, we said, could look at many dimensions at a time, you could have a multi-dimensional Gaussian that moves you in some random direction. You often end up getting a lot of rejected samples in that case. And so often you can get a proposal distribution that's a little bit better if you're if you know something about the one-dimensional distribution. Okay, so so basically, given a sequence of one-dimensional proposals, you could compare sort of the rate of movement for one at a time versus like concatenating them all together. So for Gibbs sampling, in fact, maybe sometimes it's better to sample a whole block at a time rather than just one. So maybe for both of these, in fact, the answer is somewhere in between, right? Don't sample all of the variables at once. Don't sample just one. Sample some small set of variables that you can tractably work with. Okay. So when is it tractable to sample a block of variables? Well, one of those cases is where you're sampling from a block that corresponds to the factors of a factor graph. Okay. So this is the big question. How do we actually assess convergence of the Markov chain? We just did all this theory work to show that it will converge, but practically if you implement one of these things, how do we actually know that it's converged? And well, honestly, it's kind of difficult. But one of the answers is to actually compare statistics of multiple independent chains. So here's what I mean. Imagine that you have two chains, right? And they start out at different states, and you're just watching the log likelihood of the actual samples according to your model. Or maybe something, proportional to log likelihood. That's easier. And so, you draw samples from both of these, and you start to notice that the likelihoods sort of like move up to some high probability region, and then they kind of like shuffle around in that high probability region, but kind of stay there for a while. That's often a good indication of convergence. If instead what you're seeing are likelihoods that look like these, well, then maybe you haven't yet actually converged, right? Because here it looks like there's a lot of volatility. There's a huge amount of movement, and you're still kind of in an early phase of exploring the space. Okay. So another question is, is one long Markov chain better than many short ones? Well, a couple things to note. One, it's difficult to actually discard your initial samples. This is called a burn-in period. And it's partly because the chain itself may not have mixed or sort of reached its converging distribution. And so, again, just like the whole block Gibbs sampling thing, often a balance is best, right? So if you have some amount of computation and you can either run one really long chain or a bunch of short chains in parallel, maybe your best option is actually somewhere in the middle. And the nice part is, you're getting sort of more independent samples, right? Each chain is in theory sort of independent to the other chains. And compared to this setting, if you samples, maybe 6 samples. Okay. Practically, if you're actually implementing this, you might have some parallel hardware that allows you to more efficiently, say, parallelize this stuff. And lastly, if you have multiple chains, then you have some mechanism for maybe. We're going to just kind of leave this as sort of some extra ideas, and we'll be sending out sort of a list of data set ideas before then, so that you have something to stew over. Great.